All right, welcome everyone. So what we're going to do here is we're going to take a look at some other things that we call triangle centers here. Okay, so for now, let's focus on just two segments here. So we have basically the idea is that we have three sort of major towns here, right? A, B, and C. And we want to build a hospital. And in the interest of fairness, it makes sense for the hospital to be the same distance from each of these points. So we want this to be the same distance from A to B and C. So wherever the hospital is going to be, we want it to be the same distance away from A, B, and C at the same time. That's fair. So I'm not exactly sure what to do about that, but I do know how to do this if this were two towns, right? If this were two towns and we just focus on A and B, we want to find all the points that are the same distance away from A and B. Now, if I'm not mistaken, that's not too hard because I hope that you remember something about equidistance theorems. So if we want to be equidistant from 2 points, we're looking at the perpendicular bisector here, right? So we can create a perpendicular bisector of AB. So I'm actually going to do that here. So if we do something like this here, we can create a perpendicular bisector like so. Right? We can create a perpendicular bisector like so, and do this. Now the perpendicular bisector is great because remember we mentioned that any point on this perpendicular bisector is equidistant from AB. So that means all points here, these are equidistant from A and B. Okay? So what we have here, ladies and gentlemen, is that we can kind of put this all together now. So now that we have all three, it shouldn't be too hard for us to do the same thing here. Now we're going to do the same thing. We're going to construct a perpendicular bisector for all the sides here. So I'd like you to go ahead and try that out on your own here, ladies and gentlemen. I'm just going to do that really quickly so that we can see this here. I'm going to try to be as efficient as possible, so I want to use as few strokes as I can. So I'm going to use the same. So the idea behind this is I'm going to use the same radius for everything here. Okay. Now, do note, ladies and gentlemen, this is, tricky. So you'll have to be kind of careful about it. And again, if you don't feel particularly good about this here, go ahead and do these individually. I'm just doing these all at once. There we are. So as you can see here, I've already constructed my circles like this. And now I can just look at the intersection points and do my construction. So hopefully, yep, there it is. I want my longer straight edge now. That's one. That's two. And finally here, that's three. Very nice. So now that we constructed all to be perpendicular bisectors, so it makes sense for our hospital to be in one and only one place, right? And that hospital should be exactly right here. I'll call this point here O for one and only, right? Nice. So note here, ladies and gentlemen, that we have just shown that in this situation here, O, right? So OA and OB are the same length, right? So that means these 2 points here, OA and OB, being on this perpendicular bisector, the first one I constructed, that point is equidistant from A and B at the same time, right? Similarly, OB and OC are on the same point as well, so are the same distance away as well because it's on this perpendicular bisector. We also know that OA and OC are all the same as well, right? Are the same as well because it's on this perpendicular bisector. Well, wait a minute. Hold on a minute. If that's the case here, then that tells us something important here, right? This tells us here that OA, OB, and OC are all exactly the same here. So we have this sort of situation where every single one of these distances is the same. So that means I've got A, B, and C, these three towns, they're all the same distance away from the center point O. Now, I don't know about you, but I feel like I've done this before. Haven't we seen something like this before? Wait a minute. That feels a lot like a circle, where O is the center and A, B, and C are just points on the circle here, right? So, in theory, what I can do here, if I measure OA, it should be the same as OB, O, and OC, so I can do something like this. Aha! There we go, ladies and gentlemen. Very nice. It lives! So we can see here that there exists a circle like this that I've constructed here that passes through all the points here. So this circle actually exists here. So, a couple things to note about this sort of thing here. This circle goes on the outside. So if you remember from 2 lessons ago when we talked about constructing regular polygons, this is a circumscribed circle here. So this we refer to as what is known. So this thing here is known as the circumcircle of triangle ABC. Okay? So this here is known as the circumcircle now. Now, one important thing about this here. So we note that these lines here, all 3 lines, actually happen to meet at the same point. This actually is a rarity in geometry. 2 lines intersecting at a point, that's easy. That happens all the time. But 3 lines all meeting at one point is relatively uncommon. So as a result, we give that a name here. So I can mention here, and I'll just go ahead and jot this down to the right here. We can say that 3 lines, 3 or more lines, are what we call concurrent. If and only if they all meet at a single point. Okay, so we refer to this as concurrent. And you can see here that all the perpendicular bisectors here happen to be concurrent to one another, and they all create the circumcenter of ABC here. So this is a circumcircle, right? This passes, this circle, this happens to be a circle that passes through the vertices of triangle ABC. Now, note here in this situation, something like this here. This actually works out very nicely. So we call point O here. I'm going to write this down. O, this is known as the circumcenter. So O is known as the circumcenter here, okay? So O is the circumcenter, and this is the intersection of the perpendicular bisectors of the sides. Now, we refer to this as O here. In the mathematical world, this the circumcenter pops up so often that we actually give it a name. So in this situation here, when we want to talk about this in the mathematical literature, when we refer to the circumcenter, we refer to it as O because, well, I don't know. We just call it O. We just agreed on a letter here. And as you can see, it's the perpendicular intersection of the perpendicular bisectors of the sides. Now wait, some of you may ask. Let's go back here. Notice that in this situation here, we showed that OA is equal to OB is equal to OC and so on and so forth. But technically, we didn't need all 3, right? If you think about this, if I chuck one of these statements here, if I throw this statement out, I can still show that OA, OB, and OC are all the same here from just those 2 statements. But wait a minute, OA being equal to OC corresponds to this perpendicular bisector here, correct? So in theory here, ladies and gentlemen, with the circumcenter, right? Because I showed that all these points actually are, so we can show that this point O, as you can see here, is equidistant from all 3 points here. So one nice thing about this is that since it's equidistant from all 3 points, you don't need all 3 of these, right? Since we know point O exists and it is the intersection of the perpendicular bisectors, you don't need to construct all 3. If you just construct 2, if you just construct, the perpendicular bisector BC and the perpendicular bisector of AB, that's enough. That tells you where O is, because you know the third one has to pass through that. And you can go from there. So we can actually construct this circle here by not looking at all 3 at once. We can just do 2, and that'll be sufficient for us here. Okay?